Hi dan Assalamualaikum. Today our group will present our project about thermodynamic engineering analysis. So first I will present the introduction of our project. So my name is Irfan bin Muhammad Nasrul. My number matrix CD250180. So thermodynamic is a branch of engineering that study the relationship between heat, work and energy. It's very important because this concept are used in many engineering such as power plant, air conditioning system, refrigerant system, turbine, compressor, and heat exchanger. The purpose of this project to help us understand how thermodynamic system work and how energy is transferred in engineering application. So our project is divided into three parts. The first part is about Carnot heat engine cycle. It's a thermodynamic analysis. The second part focus on applying the first law of thermodynamics to different steady flow device through several case study. And lastly, the third part explain the concept of reversible and irreversible process as well as perpetual motion machine. So next I will pass to my groupmate to explain furthermore.
Okay, I want to present the Carnot heat engine cycle. Based on the system overview, the Carnot heat engine is an ideal and fully reversible thermodynamic cycle. It serves as the benchmark for determining the maximum theoretical efficiency that any heat engine can achieve. Although it cannot be perfectly released in real-world application, it is very important in thermodynamics because it provides a standard for evaluate the performance of actual heat engine. Net, the efficiency of the Carnot heat engine given by the equation, where Th is the temperature of the hot reservoir and Tl is the temperature of the cool reservoir. This equation shows that the efficiency depends only on the temperature of the two thermal reservoirs. The greater temperature difference between the hot and cool reservoir, and the higher efficiency of the heat engine. Okay, now let's look at the temperature entropy diagram in the center. The Carnot cycle consists of two reversible processes. For one, process 1 to 2 is reversible isothermal expansion. During this process, the working fluid absorbs heat from the hood reservoir at the temperature while pro- producing work. Okay, for 2, process 2 to 3 is reversible adiabatic expansion, no heat transfer, and the temperature of the working fluid decrease from Th to Tl as we continue to the process. Okay, for 3, process 3 to 4 is a reversible isothermal compression. During this process, heat Ql is rejected to the cool reservoir at temperature Tl. Okay, for the last process 4 to 1 is a reversible adiabatic compression. Again, no heat transfer occur and the temperature of the working fluid increase from Tl back to Th, completing the cycle. In conclusion, the Carnot heat engine represents the maximum theoretical efficiency that a heat engine can achieve and serve as an important reference for analysis and improve thermodynamic systems.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Ikwan bin Muhammad Noor with CD 250058 number matrix, and now I'm going to present about steady flow devices. So firstly, the combinations of turbine and nozzle. So what is nozzle? It is a steady flow device that decreases fluid pressure while simultaneously accelerating it to a high velocity. Meanwhile, the turbine is a work-producing device where fluid expands through blades, converting kinetic or thermal energy into mechanical shaft work or work out. So, for the industrial applications, we have impulse steam stage. So it is used to generate power or marine propulsions. So high velocity steam from a stationary nozzle violently strike the turbine rotor blades buckets. The kinetic energy transfer to the rotor via an impulse change in momentum, efficiently extracting massive amounts of mechanical work. All right, done with the function and application of the device, we're moving to the case study. A steam enters at 2 megapascal at 300 degrees Celsius, expand via nozzle to 1.6 megapascal, and the outlet velocity is 300 meter per second. Assume it is adiabatic, no energy transfer, no work, and no potential energy. Find exit enthalpy and isentropic turbine efficiency. First step, so we have to compare the pressure given to the saturation pressure at 300 degrees Celsius. So out of it, we get the P given is less than the P saturation at 300 degrees Celsius. So it is superheated condition. So we have to refer superheated water table. And then we got the inlet enthalpy is 3024.2 kilojoule per kg. For the entropy is 6.78764 kilojoule per kg Kelvin. Step 2, actual exit enthalpy. So using the energy balance formula, out of the full context of the formula, we only left with H1 equal to H2 plus V2 square over 2. So this is for the actual scenario. For the result, we got the enthalpy at outlet for actual is 2979.2 kilojoule per kg. Moving on to the next step, isentropic state at 1.6 megapascal. So this have to refer to the superheated table steam in the steam table. At 1.6 megapascal, we interpolate value between 250 degrees Celsius and 300 degrees Celsius in order to get uh, the S1 6.7684. So for the result of the total calculations for the isentropic outlet of enthalpy is 2970.93 kilojoule per kg. Final output turbine efficiency, we got H1 minus H2 actual over H1 minus H2 isentropic. We got 0.84 or about 84% of efficiency for this device. Moving on to the second steady flow device, which is the combinations of compressor and diffuser. What is the functions of the compressor? It is a work-consuming device that increases the pressure of a gas by compressing its physical volume. Meanwhile, the diffuser is a non-work producing device that decelerates a high-velocity fluid, converting it kinetic energy into a rise in static pressure. So, in real life, we normally see this as a centrifugal stage, or the example we can give is the turbochargers in automotive. Another example is pipeline gas compressor and aircraft APUs. So how does it work? It rotating impeller blade violently accelerate air sideways. The unstable high velocity air then slam into the stationary diffuser channels. So the diffuser slows the air, transforming unstable kinetic energy into a massive uniform static pressure rise before entering an engine cylinder. Okay, last but not least part for me, this is the case study for second flow device. So we have air enter a centrifugal compressor at 100 kilopascal at 300 Kelvin temperature with inlet velocity of 50 meter per second. The diffuser decelerate it to 10 meter per second. So the outlet velocity is 10 meter per second. Find the temperature rise across the adiabatic diffuser. So adiabatic meaning there is no transfer heat. So Q is 0, work is 0, and potential energy is 0. For the ideal gas behavior, we have Cp, constant pressure of 1.005 kilojoule per kg Kelvin. So first step, we have to use energy balance formula. E in is equal to E out. Out of it, we only left with H1 plus V1 square over 2 equal to H2 plus V2 square over 2. So when we rearrange it, we got the differential of enthalpy H delta H equal to V1 square minus V2 square over 2. Second step, an ideal gas substitutions. So bear in mind, delta H is equal to Cp times dt. So we have to substitute Cp times dt inside dH in the previous formula. So the final output, we got temperature rise of a dt equal to V1 square minus V2 square over 2 times Cp. Putting all the parameters from the question, we got 1.19 Kelvin of temperature rise in the compressor. That's all from me, and I will pass this presentation to another person. Thank you.
To continue, we are going to define the strict physical boundaries of thermodynamics. Look at the left side of the panel under process feasibility, where reversible processes are purely theoretical, where they run infinitely slowly with zero friction. They offer maximum efficiency and zero entropy generation, where in reality, all engineering processes are irreversible and they happen at a finite rate. This where they also suffer from frictional losses and lower efficiency. More importantly, reality always generates positive entropy. Now, look at the right side of the panel where the PMM diagnostics, where we are going to use this rule to spot impossible machine of myth, where at PMM1, it violates the first law of thermodynamics, where it claims to generate energy out of nothing. This means its efficiency is falsely exceeds 100%, while at PMM2, it violates the second law of thermodynamics, where it claims that it can convert 100% of heat into work, where it rejects zero waste heat, claiming 100% efficiency, where both machines are physically impossible to exist in real life. Let's move on with our core conclusions. First of all, the Carnot cycle established the unyielding ceiling for thermal efficiency. Second, first law's steady flow analysis accurately dictates that energy transformation in devices, where this proves that with our turbine, nozzle, and diffusers calculations. Third of all, engineering must, and I must focus on this, we must minimize unavoidable losses where perpetual motion machines or devices remains a physical myth. To build on this project, our group have proposed four actionable recommendations where real gas modeling, where it moves past ideal assumptions to real gas properties for higher accuracy, Irreversibility analysis uses entropy generation metrics to pinpoint where energy degrades. Third, complex cycle integration, where expanding on individual devices calculation into full Rankine or Brayton cycles. Last of all, a sustainability assessment, where we are going to connect thermodynamics efficiency gains directly with lower greenhouse emission. This concludes our group presentation for Thermodynamics 1. On behalf of Group 8, thank you very much for watching our presentation today, and we appreciate all our support from our lecturer. Thank you very much.